We have the third of our four-part series addressing the application of alkalinity concepts. In this video example, we'll examine the relative errors associated with some common simplifying assumptions in interpretations of alkalinity titration results. So we'll examine it from two vantage points. We'll specify the inorganic carbon content and pH of a water and compute the expected value for an alkalinity titration. Then we'll specify the measured alkalinity value and the pH of a water and compute the expected inorganic carbon content and speciation of that sample. We'll examine the various assumptions made regarding the interpretation of alkalinity titration results and compute the associated errors for a specific set of cases, selectively neglecting the various components of alkalinity. As we've mentioned before, alkalinity is a measured parameter. Again, we titrate a water sample from its initial pH to pH of about 4.3 by adding strong acid. We measure and report the acid consumed. During the process, hydroxides assimilate protons to become water. Carbonate assimilates protons to become bicarbonate. Both initial and converted bicarbonate assimilate protons to become carbonic acid. And water assimilates protons to become hydronium. In part 2 of the series, we developed a corrected equation relating the measured alkalinity to the abundances of carbonate and water species, and we'll use that equation in this video example. So we'll consider the raw water of Water Quality and Treatment 6th edition, example 3.4. Initial pH 7.5, total inorganic carbon content 10 to the minus 3 molars. We'll do the computations using MathCat 15. So we have the initial and the final concentrations of the water species of interest. The initial pH yields the initial hydrogen ion concentration, the initial hydroxide concentration. The final pH yields the final hydrogen ion concentration and the final hydroxide ion concentration. So for total inorganic carbon and the carbonate system species, we'll use equations 348 through 350 rather than the alpha values from table 3.8. We'll do this for computational flexibility. We can express the bicarbonate concentration as the total carbonate times alpha 1. Then we can express the carbonate ion concentration as the total carbonate times alpha 2. First, we'll use the approximation used in example 3.4 of water quality and treatment. We set alkalinity equal to bicarbonate. We'll use our conversion factor of 50,000 milligrams per liter as calcium carbonate per equivalent per liter of alkalinity, arriving at 46.6 milligrams per liter as calcium carbonate. Then we compute the result using the full corrected equation. With pH 7.5, we can neglect the initial hydrogen ion concentration. Again, now we have our second estimate of the alkalinity using the full equation. Again, our conversion factor. Now we calculate an alkalinity of 49.3 milligrams per liter as calcium carbonate. So we compare the two results using the percent relative error, and we find that that error is about 5.4%. Certainly, if we can avoid it, we'd not accept such an error in any of our engineering computations. So let's examine a water with 1/10 of the inorganic carbon, 10 to the minus 4th molar. So we have the calculations of our initial bicarbonate, initial carbonate. We have our approximation consistent with example 3.4 of water quality and treatment 6th. We have our result from the full equation. We see that the error now is 35%, which is quite unacceptable. And of course, as the inorganic carbon content is decreased, the error of the approximation increases. So now let's examine alkalinity from the vantage of the laboratory test itself. We assume attainment of carbonate equilibrium within the water sample, both under initial and final conditions. We combine the bicarbonate-carbonate equilibrium, that's equation 347, with the alkalinity equation, and we find that we can write this with essentially a single unknown, the bicarbonate concentration. We solve this for bicarbonate in terms of alkalinity, hydroxide, final hydrogen ion concentration, and of course the relationship between bicarbonate and carbonate. Then of course once bicarbonate is known, we can determine total carbonate as the bicarbonate concentration divided by alpha 1, equation 3.49. Of course, we've demonstrated here that the inorganic carbon can be determined from a combination of measured alkalinity and pH. We need not know both alkalinity and acidity as suggested in the discussion associated with equation 356 of Water Quality and Treatment 6th edition. So we'll examine two approximations. Let's neglect hydroxide, carbonate, and the final hydrogen ion concentration, and then let's neglect just the hydroxide and the final hydrogen ion concentration. So let's examine measured alkalinity values of 50 and 20 milligrams per liter as calcium carbonate. We have the first approximation omitting carbonate, hydroxide, and final hydrogen ion concentration. We have the second approximation omitting only the hydroxide and the final hydrogen ion concentration. And of course we have our what we'll consider the true value, which includes the hydroxide, the final hydrogen ion concentration, and both bicarbonate and carbonate. When all is said and done, the error of the first approximation is 5.6%. The error of the second approximation is 5.3%. We see that there's not a lot of difference between the two. If we look at the 20 milligram per liter as calcium carbonate measured alkalinity, we won't go through all of the steps. We see an error of the first approximation is 14.8%, and an error of the second approximation is 14.4%. None of these errors are very acceptable in light of what we'd like to see for most engineering calculations. We observe that for low alkalinity waters, when we neglect the acceptance of protons by water to form the hydronium ions during the titration, we have some very unacceptable errors in the interpretation of alkalinity titration results. Then in part 4 of this series, we'll compute some relative errors associated with these simplifying assumptions for a continuous range of measured alkalinity values from a few to several hundred milligrams per liter as calcium carbonate.